It is now my pleasure to introduce our keynote speaker, Dr. McCauley. Please join us at the podium.
Thank you very much. I'm going to talk to you today primarily about the heart. But what I'm going to tell you today is going to be applicable to any organ around. So, as you all know, there is mitochondria in every cell of the body except for the red blood cells. And in the heart, they're particularly present. They're 30% of the cell volume. They provide all the energy for the heart to contract. And to do this, they use oxygen. There's only two reasons we need oxygen. Start a fire and allow us to present electron donors through that electron transport chain to produce energy. If you stop that oxygen coming in, or if you end up with a deletion where the energy production is stopped, you end up with what we get called as ischemia reproduction injury. It's the #1 killer in hearts around. And a lot of you who have children who have mitochondrial myopathies, this will be one of the problems that you'll arrive at later on. So this is what a normal mitochondria looks like. It's round, electron dense, and you can see these little cristae there. This is a piece of muscle fiber. This is a nucleus. And the mitochondria are gathered around them. And after 30 minutes just of ischemia, this is what they look like. The mitochondria become really enlarged. They become electron translucent. They get the cristae, their insides are all broken up. This is calcium accumulation that occurs within them. And you can also see, once they start going, the tissue erupts, splits, and everything else. And you end up with a cascade of events that causes injury. And all of these events occur when you stop the oxygen delivery or in the ischemic phase. And even when you bring back the oxygen and try to get the heart tissue going, these persist and you end up with decreased cell viability and the heart doesn't function very well. So for years, people were looking at how do we fix this? So they were going either upstream of the mitochondria, picking up various protocols, using various agents, or they were going downstream of the mitochondria. And quite frankly, none of these work very well. And I've used some of these. These were the popular things, what to do. Then around 2007, we were thinking, well, why don't we look at the organelle itself? Why don't we look at the mitochondria itself? Why don't we take mitochondria from some area within the body that are healthy and then isolate them from the tissue, deliver them back into some area where the mitochondria were damaged to help the heart recover. And it was a flyer at the beginning. It was something we had thought about. It took us about two years to gather and figure out what we were going to do. And the first time we did it, it worked perfectly. Heart came back from a gray mass that was very fibrillating, went into pink and came back immediately. We presented that data in 2009, and we've expanded. So, no matter what anybody tells you, surgeons are not, calm people. They do not like to wait. And at the earlier time when we started, it took about 2 hours to isolate mitochondria. And it was a process where you essentially centrifuge down a whole bunch of debris over and over and over again. And it was not very clean product. So we ended up developing a quick methodology for isolating the mitochondria. It just uses not a series of filters. And we do this on the bench right beside the patients. So we take out 2 small pieces of tissue. There they are. This is an American dime. And we take out these 2 just using a number 6 biopsy measure. So if you go to your dermatologist, you have some sort of lesion, you think it's possibly cancerous, they'll pop that out with a number 6, and then they just put a butterfly to close it up. That's what this is. We take 2 out because when the babies first started this, some of the babies had ischemia and the tissue was bad, and we had to trim it around. But if you have a normal piece of tissue, one of these will do. And you can get them from the various sites. If you're going in, wherever you're going in on the patient, you can get the tissue from it. It doesn't make any sense if you're doing a cardiac event going in with a medial cut down or mini thoracotomy going in here to take them from the liver. That's a secondary source. So if you're going in through the neck, you get sternocleidomastoid, there's a muscle right there. If you're going in from the chest wall, you can get from chest muscle, pectoralis major, wherever you want to go. And you know, almost every patient now has a cut down for femoral vein catheter going in. These guys are, you know, I'm quite a bit older than my technicians. These guys with catheters, used to games, they can maneuver around a catheter, you know, just up and down and everywhere to get there. So from those 2 pieces of tissue, we end up getting about 10 times 10 to the 10th mitochondria. We only use 1 times 10 to the 9th, so it's 10 times more than you would ever need. The mitochondria are all the same size. They're very pure. They're very still maintain function. Here it is, just there, and they work. They're excellent. What we found earlier was that this is required. The mitochondria have to be intact. They have to be viable. They have to be respiration competent. You can take total mitochondria. You can take interfibrillar, subsarcolemmal. Doesn't really matter. You can take them from heart, you can take them from the liver, you can take them from you, take them from me, put them in. There's no immune, no inflammatory response. Dead mitochondria, mitochondrial parts, mitochondrial DNA, respiration incompetent mitochondria just do not work. These are HeLa cells, and these are going into a heart. These are HeLa row cells where the mitochondrial DNA is damaged. They just don't work. Now, it's the same thing if you take it from fast twitch or slow twitch muscle. Here is like from soleus, which is a muscle in the back of your leg. It's a slow twitch muscle. We get the same effect as that. There's an intermediate muscle that contains both, or a gastrocnemius, which is always fast twitch. So it doesn't matter where you get these, they all go in. Once we isolate them, you can deliver by a number of methods. And these are very simple. We just take those mitochondria that we've isolated out, and we can either inject them by direct injection. And this is mitochondria that we've labeled with F8, radioactive label, F18 rhodamine. And we also added in iron on them. So this is the MRI. So if you see direct injection here, it stays fairly localized. Doesn't move. This is just a stainless steel suture that I put in there just to show you, give you a landmark where one of the major arteries is. The other way of doing this is to inject them via catheter. So if you inject them with a catheter, you can go right in directly to that organ. And you can see here, we've injected them into the left ventricle. This is the right ventricle, by the way, over here. That's how thin it is, that's the inside. And you can see, you just get them into that area. This should have been a movie, and for some reason it stopped on me. It doesn't really matter what tissue you put them in. They go into both viable and ischemic area. So here's non-ischemic area. You can see the mitochondria all going in. They do go into some area that's been damaged. They go in there preferentially. And that's because that area has been damaged and the cells are a little changed. So you do get a little bit more going in there. Now, you might think, well, if you're going to inject these in, they're going to go all over. Well, in fact, they don't. This is a 200 kilogram pig in which we injected in all at one time, by mistake, 10 times the amount of radioactive labeled mitochondria as we normally do. My fellow was a little excited at the time she was pregnant, and when I gave her 50 mils thinking she was going to jam in 5, she jammed in all 50 mils. And this is an experiment that actually started in the morning, and it went from Brigham Women's with radioactive material over to Boston Children's, and you're watching your money just blow out the window all the way through, and then we had to time this with this pig, deliver the pig into the MRI unit that we and the PET scanner that we had down in the basement, smuggle this pig through the basement so the patients didn't get worried. So anyway, when she slammed all that in, I was sort of upset. But it's nice to wear a mask at those point in times. So you can see, here's the mitochondria. They're all in the heart. Once you inject them, they go to that area. So here is the mitochondria that go into the cells. This is just the heart at various levels. And this works the same thing. Here it is. This is a 100-kilo pig again. This is into the kidneys, through the renal arteries. You can see the cells. Here they are. Here's the mitochondria. And here's into the lungs. The lungs are kind of interesting because we can either put them in through a pulmonary artery, which you can do when the chest is open, or we can do it by aerosol. And it goes in very well. And the only difference is when you do vascular, you don't get through the trachea and that, and the bronchus isn't lit up. Whereas aerosol, everything gets lit up. They go to all the cells. So you can get mitochondria into everything. And here, this is just into skeletal muscle where we inject them, and they stay there. You can see the mitochondria. They're in the various ones that get taken up by all of these, and we've had all of these different cell types that go in. So how do they go in? Well, it's a billion-year-old process. 5 billion years ago, we were a cell that was essentially a slug working around. It had didn't use any oxygen. The only way it got its energy was by fermentation. So you have a drunken, sluggy cell moving. The way we expanded to where we are now was another cell that used oxygen, made a lot of energy, merged. That ended up with multicellular environments, and individuals allowed us to progress to where we are. This is a theory put together by Lynn Margulis, and I wish she was around. She passed away just prior to our first experiments here. So anyway, they go in, usually this is human mitochondria that we labeled with immunogold. And we used human cells here. The reason why we wanted to use human cells is because we want to put this into the patient. We don't want to be sitting around worrying about, well, okay, it works in an animal, but can we get this into a human at the same time? So here it is, you can see, here's the mitochondria. This is at 5 minutes. We did this at 2.5, 5, and 10 minutes just to show the uptake. 2.5 is the shortest time period we could do this because we just couldn't stop the reaction fast. So here they are, right adjacent to the cell. You can see them being engulfed by the cells. And here's the cell, mitochondria all inside the cell. And this is, again, 5 minutes. So they go in rapidly and go into those cells, and then once they're there, they stay. So this is actually a movie, and this was all done by a colleague of mine who was locked in a room over in Harvard, over at the center, and Doug Cowan did all of these. What he did was he labeled human cardiac cell line with all of their mitochondria was red. And he labeled another cell line green. Isolated those green mitochondria and put them into those cells. And this is what you can see. Here are all these mitochondria coming in. This is a nucleus right here. And you can see those mitochondria coming in, they fuse with the other mitochondria. And once they fuse, there's a number of processes that go on. So that paper actually showed, you can see the mitochondria that go in, They join with a early endosome, they get released. They go to late endosomes, get released. And then they go off and they fuse. You can see them actually fusing here with the other mitochondria. And they fuse close to the nucleus. And that'll come up pretty early later on. The mitochondria contain all the fusion proteins. They don't contain any fission proteins, I mean they're splitting apart. And they're not decorated with Barkin. So they go in, they're not destroyed, they within the cell very rapidly. And if you look at the cells, 3D, you can see here's the nucleus, here's the mitochondria, all located around the nucleus in a very close area. This is just give you the depth of analysis. Once you put them in, we find them, early time period. Here they are at 2 hours. You can see them at 3 days and at 28 days. I will show you data to 28 days. The reason why we go to 28 days in our animal studies is after that the animal quarters want us to get rid of them to allow other people to come in. So I could send my animals to the, Ritz-Carlton or something. But so the 28 days is the end point. And you can see they're still functional because here's the cells that just got vehicle. Their ATP is low, but here's the amount of ATP that's being generated by all of those mitochondria within there. And we only use ATP as a marker. It's a mitochondria. It's producing ATP. That's why we use that as a marker. When you deliver the mitochondria, it's perfectly safe. We've had no problems with them. We've checked about delivery through the coronaries. They don't cause any clogging. Even if you constrict those coronaries with what's called ADH, or you constrict them plus put a load on them with epinephrine, there is no, they just completely, they work when there's no problem. There's no arrhythmia with them. If you put in stem cells, that was the early problem with stem cells, they would cause a little focal arrhythmia or something. So this doesn't happen. You also get no inflammatory response, and the reactive oxygen speech itself. So the other big thing is that there's no serial, no reactive immune response, whether you do a single injection or serial. So if we give you one injection, or multiples right after, or multiples delayed, you have no immune response. There's no acute alloreactivity, etc. No chronic allorejection, etc. They're fine. We also get no autoimmune response. Some patients with primary biliary cirrhosis get an autoimmune response to their own mitochondria, and we wanted to check, well, if you're adding more mitochondria, does this happen? No, it doesn't. We also get no effect onto the tissue, no damage response. Circulating free mitochondria is the same, there's no increase versus control. And here it's just tissue, and you can see the various, this is just an H&E, this is a mast cell trichrome, and this is electron microscopy. You can see the tissue is fine, and this is 27 days later. The amount of mitochondria we need is quite small. We don't need the millions of mitochondria that are needed, that are present within that skeleton. You only need a tiny percentage. 0.1% is what we are approximately given. We can get it up a little bit higher than that. What we find is, here's the various concentrations. This is in a heart. Here's dead mitochondria going through here. This is coronary. Here's 1 times 10 to the 3. You see you get very little. And it starts to ramp up. The maximum we get is here in the red. That's 1 times 10 to the 9. You can add 1 times 10 to the 10, but it doesn't give you anything better. So this is all in the heart. And this 1 times 10 to the 9 is good for the lungs, good for the kidneys. Skeletal muscle, we need a little bit more. So if you were looking onto a child for reaction on this, you might put in 1 times 10 to the 10. within that bulk of muscle tissue. Now we've done this primarily in the hearts, and all of our early study was in pig hearts. And the reason we use the pig is that it's the same size as the adult, human adult. It has the same architecture. My guys are all cardiac surgeons. All those fellows come in, they use the same equipment that they're using on patients. So they can go right from our lab right into patients providing these operations. The other reason we use a pig is because it's very sensitive. If you make a mistake during that period, the heart will fibrillate or it'll stop working and you're in trouble. So what we normally do is cause a temporary regional ischemia right here across this artery, and just by a snare. And at the end of 30 minutes, we release the snare. And then we let the heart reperfuse either for 2 hours or 28 days. And at the end of it, we give either an injection of just vehicle or we give it mitochondria. And what we found is, well, if you give it the mitochondria, it preserves the viability and everything else. You get decreased cell death and decreased rods. The function is quite evident, and you end up with an increased ejection fraction, systolic shortening, and the heart actually uses oxygen much better. Now, I didn't want to show you a bunch of slides on this. Your eyes may be glazing over now, but anyway. Here's what an injured heart looks like. This is a pig heart, by the way. It's blood perfused, it's on a ring. So here we are. We're just injecting in a little bit of mitochondria there. This is what it looks like after it gets the mitochondria. And that goes on for 6 hours. On the rig. At the end of 6 hours, we just stop. So this is in lieu of a bunch of graphs that I can show you. This works for neonatal hearts. It works for pediatric hearts. It works for adult hearts. It works for skeletal muscle. We've done this on rats that have gone ischemia reperfusion on the limb. They run faster than the normal animals right afterwards. We've done this on aged animals that have, sarcopenia, which is just the muscles are totally wasted. On day one, they come back running 50% faster and 50% longer than their other cohorts. And we've also done it on rats that have what we train to be sedentary. They're bred for a long period of time, and they're sort of like the sludgy cells that you've got further on. So one of the big things here is once you put it in, there's a number of effects that you initially see, and these are really easy. This is instant gratification for a surgeon. If we had done this on some other organ, you wouldn't have been as plain and done. Once we do this, it comes within 5 to 10 minutes. The surgeon can see this. So this sells it quite well. And you end up here, it's lasting. This is at 28 days again. Here you can see this is left ventricle, and you can see this is where the injury had occurred. You can see this isn't functioning very well. This is just amylines, and you can see here, these amylines are really scattered, are really close, not looking very, very well, whereas then here is the one that got a mitochondria. You can see it's contracting very well. And the big thing here is 28 days is still, mitochondria are still functioning, and they're functioning well. One of the ways this works is it changes around the transcriptomic and proteomic mechanisms in the heart and in other organs while they're at. We end up with the mitochondria being upregulated, similar to what we've got in the vehicle. This is at 2 hours, 28 days. You can see here's the one with mitochondria. Here's vehicle and the control. You can see the mitochondria are upregulated. Proteomic people have a code of their own. Green is down, red is up. They obviously don't want to drive behind a proteomics person. So anyway, this is metabolomics, and you can see that it's upregulated and comes back on normal. Here we are. What we find is, in about 2 hours and 28 days, we end up with a significant upregulation of some pathways. These are mitochondrial dependent pathways. We get upregulation of anti-apoptosis, means rejection of cell death, muscle development, muscle contraction, cardiac development, RNA biosynthesis, and then stuff to do with the mitochondria. And we get surprisingly downregulation of apoptosis, DNA damage, proteolysis, and this is fatty acid metabolism because you switch over when you get this. We also get upregulations for mitochondria, skeletal muscle nucleus. Doesn't matter what tissue that we've looked at, we seem to get a lot of homology between all of these mechanisms. Every time it's anti-apoptosis. And if you look at what's causing these changes, it's the mitochondria. It's not something else. It's the mitochondria that we put in. This is both transcript. These are how did those pathways get increased with the RNA through the mitochondria. As those pathways get increased with the proteins, that was mitochondria. So it's nice to have all this data, but what does it do? So we've actually done this on a group of patients who were congenital heart defects, and this is one we can readily show you. This is Mother Jennifer, and this is our baby that we've had since this is her when we just started off. If you go to the website, it's Baby Avery, and it's quite a tear-jerking movie that they put out. Anyway, these children have congenital heart defects that come in, and they have major operations that are coming in. And it takes a long period of time. So you can't work on a heart that's beating and there's a lot of blood in the area, so you have to stop the heart. There are various methods to stop the heart. We can do it for 45 minutes, but sometimes these procedures go much longer. And if it goes longer, you end up with the heart not working correctly. So what happens is, once you bring it back, the heart is not able to push the blood around the body. There's a couple of ways of doing this, of supporting this. You can either put the child on pharmaceutical support. Everybody knows about nitroglycerin, verapamil. Okay, and but they don't work very well. So the other way is put them on ECMO. And this is what it looks like when you've got a child on ECMO. Here's the child, and you can figure there's going to be about 15 people running around here. And it's quite a crowded region. So what we were able to do was, we were able to get patients and treat them with the mitochondria. And this is the setup that we have right at the end of the bench. It goes right there. We had no effect on safety assessment with any of those children. What we did find was, if you gave them mitochondria, they got off the machine. We got 2 of them off the machine. Their functional recovery was only 2 days. Took them to recover once they got the mitochondria. Whereas it was 9 days for the ones that got the control. And this is historical. We don't say, oh, we're going to give you one baby mitochondria. So, and successful weaning from ECMO, within those 2 days, we got 8 versus 4 out of 14. The other thing is, at the time of their hearts were working very poorly, -6 to -23. You've got to remember, more contraction is more minus. So anyway, here it is, time of treatment was the same with these, but after we gave them mitochondria, it was -23. -20 is normally what you people would have, everything else. So this is what prior to mitochondria looks like, and this is what it looks like 24 hours out. And this This happens all the time. But the big thing here is 80% success rate on these children, whereas normally 89% failed, and we only had a few recover on that. So at present, we've used this, it's a little late, we've done this on 16 children. We've got over 80% of efficacy on this. We have no safety effects. Those kids are still going around. And this is baby Avery, now who's gone through a complete terrible twos and was recovered. We've had a lot of luck with this. We have a lot of collaborations with various people, and it's working and everything. So today, I think you will see how those collaborations work and where we can go. Thanks very much.
And so in our tradition, we're going to reserve our first question for a patient or a family. And I'm just wondering, Kara, is there a patient or family that would like to ask a question?
I'm not a patient, I just have a question.
Well, you got to hold on then. Kara? All right, you get to go. You got to speak really loud so everybody can hear you.
So is it a one-time treatment or it's like a lifelong opportunity?
It can be one time on all of those babies, and nobody's come back. They're all living, they're all functioning perfectly now. We've never had them come back for any change in the heart. The heart's still working. Those kids, all of those kids are running around, their heart is doing well. They've never had to come back and be put back on a support system or any drugs to accentuate what they were doing.
Okay, thank you. Dr. McCulley's around for the whole next 2 days. Ask all kinds of questions.